Hi everyone, good morning. So let's start. So in this lecture we will study matching. This concept we will study. But before we study this concept, let's do some questions on so we have already seen independent set and covering. Covering means vertex cover, edge cover. These two things we have seen. And we have seen what is covering number. What is covering number? Covering number. Can anyone tell me what is covering number? Covering number means the size of minimum vertex set. The size of minimum vertex set. Okay, very good. Anurag, very good. So that is the idea. Now let's see the first question. Okay, think about this question and tell me what should be the answer. What should be the answer? By default, minimum vertex covers. Yes, Preeti, very good. So tell me, think about it. See, let me tell you one thing. Let me tell you clearly, let me tell you one thing. In the GATE exam, they can ask you new question. Okay, like every question will not come directly from the notes. Concepts will be from the notes, but questions can be new. Okay, so whatever question comes in the GATE exam, whatever, you have to apply your concepts. Every concept we have seen, just apply your concepts. So for this question, you try. For this question, apply your concepts. We have seen all the concepts that you need to know to solve this question. Assume this question comes in the GATE exam, then what you will do? Think about it. So this question is saying that minimal. Okay, first of all, remember here this word, focus on this word, minimal edge cover. The question is talking about minimal edge cover. Okay, the question is talking about minimal edge cover. Okay, minimal edge cover of a graph can contain 3 edges of a triangle. Tell me, is it possible? If you have a minimal edge cover, let us assume you have a minimal edge cover. Is it possible? Let us assume you have a minimal edge cover. Your edge cover is minimal. You have a minimal edge cover. So let's denote this by minimal edge cover. Okay. So tell me, if you have a minimal edge cover, in this minimal edge cover, is it possible? To contain is it possible to contain all the 3 edges of a triangle, like all the 3 edges, like AB, AC, BC? Okay, is it possible that you have all the 3 edges of a triangle? You have a triangle ABC. Okay, this is your graph. In this graph you can have something else. Okay, you can have something else. In this graph you can have something else. I don't care, you can have more. You can have more vertices, you can have more edges. Okay, so this graph can have something else. Okay, but I'm asking, is it possible that this minimal edge cover, it can have 3 edges of a triangle, like this type of triangle you have? Can it contain 3 edges of a triangle? Is it possible? This is minimal. Remember, this is minimal. So why this is not possible? Why this is not possible? So the statement is false. Very good, the statement is false. But why this is false? Tell me. Because this is minimal. Focus on the word minimal. This minimal word, focus on this word minimal. And remember, because it is minimal, so you can remove this. See, you can remove, for example, you can remove this. Yes or no? This BC, these two vertices are already covered. B comma C, these two vertices are already covered. This is unnecessary. This edge is unnecessary. I can say one of these edges is unnecessary. One edge can be removed. Very good. Abhipsa, very good. Okay, so basically one edge can be removed. One edge can be removed. Can be removed. One edge can be removed because, for example, if I remove this edge, let me remove this edge. Okay, still you can notice that we are covering still A comma B comma C. A comma B comma C. These vertices are covered. Okay, so you can remove one edge. For example, you can remove this edge. Still you can notice ABC are covered. Okay, so I can say finally that one edge can be removed. So this is your answer. So that is the reason the answer will be false. Okay, answer will be false because one edge can be removed, so not minimal. So this is not minimal edge cover. So not minimal edge cover. Okay. So like this you can, okay, you can solve this type of question. Tell me about this one. Tell me about this one. Minimal edge cover. Again, the question is talking about minimal edge cover. Minimal edge cover of a graph can contain three edges of a path. Can contain three edges of a path. Is this statement true or false? So minimal edge cover, your minimal edge cover, can it contain three edges of a path? Three edges of a path means, for example, AB, BC, CD. Three edges of a path. I am talking about a path here. Is it possible that you can contain three edges of a path? For example, let's assume this is your path. Okay, remember, in your graph, you can have something else. You can have something else. A, B, C, D. You can have something else. You can have something else. I don't care about something else. Okay, so in your graph, you can have something else. But tell me, is it possible that in the minimal edge cover, is it possible that you have three edges of a path? Like these three edges of a path. Is it possible? Again, the same logic you can apply. What will happen here? One of these, which edge can be removed? One edge can be removed. Which edge can be removed? So in this previous question, any one edge can be removed. Here any one edge can be removed. Okay, in this question, which edge can be removed? This BC edge can be removed, right? I can remove this BC edge. See, this BC edge is not covering uniquely. Like this BC edge is not covering anything uniquely. This is not covering anything uniquely. You can remove it. If you remove it, there is no problem. All the vertices are still covered, because you can notice B is covered here, C is covered here. So that is the reason I can say that this BC edge can be removed. Okay, BC edge can be removed. Can be removed. So not minimal. So not minimal edge cover. Okay. So this is the idea. So actually this is a university question. This was a university question. You can notice that they have given the definition, and then they are asking that show that a minimal edge cover of any graph contains no path of cycle, no path of length 3 and no triangle. Okay, so this question we have seen. This question we have done. In the last class we have seen this. Agree? In the last class we have seen that if v dash is vertex cover, then v minus v dash will be independent set. This we have seen in the last class. Okay, tell me for this question A, B, C, D, E, for this what will be the vertex cover, like smallest vertex cover? So what will be the smallest vertex cover? The smallest vertex cover will have total 3. You need total 3. Smallest vertex cover, that will be, this will be your smallest vertex cover. So I can say what is beta of this graph? What is beta of this graph? That is 3. Okay, and what is alpha? Alpha means independent set. Alpha means largest independent set. So the largest independent set, that will be basically, I can say, for example, B comma D. This is the largest you can create. Your beta is 3, then your alpha will be 2, because we already know that alpha plus beta is equal to number of vertices, for any graph. This we have already seen in the last class. Let's see the next topic, that is matching. Okay, now what is a matching? Matching is basically edge independent set. Okay, so do I need to give you the definition now? Yes or no? See, matching is basically edge independent set. What it means, can anyone tell me? Edge independent set means set of edges which are independent. Set of edges which are independent means set of edges which are non-adjacent. Okay, so let me tell you these concepts. If you notice, some concepts are for vertices, some concepts are for vertices, and some concepts are for edges. So which are the concepts for vertices? For example, this vertex cover, this is a concept for vertices. Yes or no? So this vertex cover is a set of vertices which will cover all the edges. This is set of vertices which will cover all the edges, and the corresponding concept we have in edges here. What is the corresponding concept? The corresponding concept is edge cover. Correct? There is a corresponding concept here, that is edge cover. What is edge cover? This is set of edges which will cover all the vertices. So you can notice this is a concept for vertices, this is the concept for edges. Here set of vertices which will cover all the edges. Here set of edges which will cover all the vertices. Another is independent set. Independent set. Okay, this is independent set. So basically what is this independent set? This is basically vertex independent set. What we are talking about, this is a set of vertices which are non-adjacent. Set of vertices which are non-adjacent. So I can say this is a vertex. I can say this is a vertex independent set. I can say this is vertex independent set. And what is the corresponding concept for edges? What is the corresponding concept? Here you have vertices adjacent, non-adjacent vertices. So you need non-adjacent edges. This is the concept, matching. This matching concept means basically this is the concept which says that edges independent set. Okay, edges independent set means edges which are non-adjacent. So this is the idea, very simple. So remember, these are the concepts for vertices, these are the concept for edges, these are set of vertices, these are set of edges. Okay, so very simple. Now let's see the definition of matching. Already you know what is the tell me, if I give you a graph, when can I say two edges are adjacent? We have already seen this. When can I say two edges are adjacent? For example, this E1, E2, E3, E4, E5. Tell me, what are the adjacent edges? What are the adjacent edges? For example, E1, E4, these are adjacent. Adjacent means they basically share a common endpoint. They share a common endpoint. See, E1 is basically, what is E1? E1 is AB. And what is E4? E4 is AD. So they are sharing a common endpoint. Okay, a common endpoint. They are sharing a common endpoint. What about E2, E5? What about them? Remember, E2 is basically AC and E5 is basically BD. They are not sharing any common endpoint. There is no common endpoint. Okay, very simple. So two edges are adjacent. This definition we have already seen in the first class of graph theory. So you can check. Adjacent edges means if they share common endpoint. For example, I can say that E1, E5, these are adjacent because they share this common endpoint B. Okay, so this is the idea. Now let's see the definition of this matching. What is the definition of matching? This is set of pairwise non-adjacent edges. Non-adjacent edges. As I told you, this is edge independent set. This is the definition of matching. Okay, and similarly, what is matching number? What is matching number? Matching number means the size of maximum matching, the size of largest matching. Okay, that will be the maximum matching. So let's take with example, this concept will be clear. So let's assume that you have a graph like this. So let me give you a graph. A, B, C, D. Okay, E. So let's assume this is your graph. So can anyone give me a matching? Can anyone try? Give me a matching. Matching means set of edges which are non-adjacent. Set of edges which are non-adjacent. So give me a matching. So you can notice that set of edges which are non-adjacent. This is a matching. You can take only one edge. If you take only one edge, that is fine. There is no problem. Set of edges which are non-adjacent. So you can take one edge. Okay. So can I tell me BE, is this matching? Is this matching? This is not matching. You can clearly see that, okay, this is not matching. You can clearly see that this is not matching. Okay. Next, tell me AB, CD. Is this matching? Yes, this is matching. See, you don't have to see the graph. Just look at here. All the vertices are different. See, all the vertices are different. A, B, C, D. All the vertices are different. Here you can notice this vertex B is common. So this is a matching. Okay, this is a matching. What is the largest matching you can create? What is the largest matching you can create? Can you create largest matching? I think, okay, the largest matching will have size 2. For example, I can take BE, AC. This is what I can take. Okay. So anyway, this is also matching. So this is the idea. Okay. What is the concept of matching? Matching means, what is matching? Matching means non-adjacent edges. Very simple. Non-adjacent edges. Non-adjacent edges. This is the concept of matching. And let me take another example. For example, E, F. Okay, so let's assume this is your graph. Now what will happen? Give me the largest matching. Can anyone give me the largest matching? What is the largest matching that you can create? What is the largest matching that you can create? AC, ACBDEF, ABCDEF. Yes. Okay. So you can create like this. You can take AB, CD, EF. Very good. You can create only this. See, just think about it. Okay. Please think about it. Can you create something more? Can you create bigger? Can you create bigger? No, you cannot create, because already whatever, if you create bigger, then already all the vertices are already you have all the vertices. Already all the vertices you have. No, this is not a matching. A, B, B, D, E, F. This is not a matching. This is not a matching. See, this B is common. See, this B is common. Okay, here you can notice all the vertices are different. Notice all the vertices are different. So this is matching. Notice all the vertices are different. Okay. Okay. Is this clear? So this is the idea. So remember matching. Matching basically, in matching what happens? In matching what happens? Matching is like a set of edges. Okay, matching is like set of edges. So you have set of edges. For example, let's assume E1. This is, let's assume A1, A2. Okay. Or maybe I can say this is, let's assume A1, B1. E2, let's assume that is A2, B2. E3, let's assume this is A3, B3. Okay. So tell me one thing. If this is matching, if this is a matching, if this is matching, then what should happen to, okay, is it possible that they can be same? If this is a matching, then what should happen? If this is a matching, if this S is matching, then these six things must be different. Yes or no? These six things must be different. These six vertices all must be different. These six vertices must be different. Must be different, correct? Because it is a matching. It is a matching means, oh, okay, edges are non-adjacent. It is a matching. Matching means edges are non-adjacent. Means there is no common endpoint. There is no common endpoint. So all these six vertices, they must be different. These six vertices, definitely they must be different. Similarly, if I have, for example, let us assume if I have, and so on, if I have En, and that is An, Bn. Now what should happen? So here, all these, I can say, all these, how many? All these vertices must be different. All these vertices must be different. This is the idea of matching, because in a matching you should have non-adjacent edges. Non-adjacent edges means there should be no common endpoint. You should not have any common endpoint. Okay. So let's see this this Cn. For Cn, what is the matching number? Remember what is the matching number? The concept of matching number. What is matching number? Matching number means size of largest matching. This is the size of largest matching possible. Largest matching possible. Okay. Size of largest matching. That will be your matching number. So tell me one thing. What should be the symbol for it? Like, okay, what do you think? What should be the symbol? What should be the symbol for it? So the symbol for it is alpha dash G. The symbol for it is alpha dash G. Some people also use this symbol mu G. Okay, some people also use, see, if you notice one thing, see, this vertex cover has what symbol? What is the notation for, what is the symbol for vertex cover? That is beta of G. This vertex cover symbol is basically beta of G. So this is your beta of G. So edge cover symbol is what? That is beta dash of G, because they are corresponding concept. This is the concept for vertices. This is the concept for edges. Similarly, for independent set, the symbol is alpha of G. Alpha of G. And for matching, the symbol will be alpha dash of G. Okay, very simple. So like this, you can remember, very simple. Vertex cover has symbol beta of G. So edge cover will have beta dash of G, because they are the corresponding concept. This is the concept for vertices. This is the corresponding concept for edges. Here vertices will cover edges. Here edges will cover vertices. Here you have non-adjacent vertices. Here you have non-adjacent edges. So like this, you can create the symbols. Okay. Now, so matching number means size of largest matching. What is the largest matching you can create? That is your matching number. So let's see the matching number of this is Cn. So tell me, what is the matching number of this C3? For C3, what is the matching number? Matching number, I can say mu. Okay, I can say mu. What is the mu? Matching number. How many edges you can take? See, only one edge you can take, right? Only one edge you can take. You cannot take more than one edge. Only one edge you can take. So mu will be 1. If I have this graph, for this graph, what will happen? Now you can take 2 edges. Okay, now you can take 2 edges. For example, A, B, C, D. A, B, C, D. You can notice all the 4 vertices are different. So here mu will be 2. And what if your graph is like this? If your graph is like this, again mu will be 2. And if your graph is like this, then your mu will be 3. So what do you think? What is your mu? What is the mu? So for Cn, mu is what? That is n by 2. That is n by 2 floor or seal. That is n by 2 floor or seal. That is n by 2 floor. Okay, n by 2 floor. So very simple. Half, because here you have 6 vertices. So your mu is actually 3. So basically you are getting half. Okay, so mu will be n by 2 floor. Very simple. Now let's see the concept of perfect matching. Let us see the concept of perfect matching. Perfect matching. The name itself is telling you this is a matching which is perfect. This is a matching which is perfect. Okay. In the real world, when, okay, this word matching, when do we use this word matching? In the real world, when do we use this word matching? Matching in real world. Matching in real world. On the matrimonial sites, right? Yes or no? On the matrimonial sites, marriage, for marriage. Yes, this is like, okay, this is not a job. This concept is actually useful in the marriage. There is a marriage problem. Okay, once you go to MTech, okay, you take the algorithm course. For example, in IIC Bangalore, you take the algorithm course there. The first concept they will teach you is matching. This is the first concept they will teach you. Why? Because the first algorithm they will take is marriage problem. So there are men, there are women, okay, and the marriage problem. So basically, if you notice, like for example, let's assume there are men, and let's assume here you have women. So for example, maybe M1, M2, M3, and let's assume you have women, W1, W2, something like this. Let us assume this M1 likes both of them. M1 likes both of them. Okay, so this M1 likes both of them. And let's assume, so something like this. Okay, this is basically, this will be a directed graph. But anyway, what I'm saying that, okay, so this type of graph you will get. Okay, this type of graph you will get. So let's assume, okay, like this. Then finally, what we want what? Tell me, can anyone tell me what we want from this? Like, okay, do we want this? Like M1, W1, M1, W2? Do we want this? M1, W1, M1, W2? Do we want this? This type of situation do we want? We don't want this, right? We don't want this type of situation. Okay, correct? Okay. So now, so finally I can say that, okay, so this matching you can very easily understand from the marriage situation. From the marriage situation, what do you want? You want, for example, maybe if, for example, M1, W2, okay, W1, M3. So something like this we want. What we want, something like this we want. Is this clear to everyone? So this matching, you can very easily understand this matching from the marriage situation. From the marriage situation. So basically what we want, we don't, these vertices must be distinct. They must be different. Yes or no? You should not have common endpoint. You should not have common endpoint. You should not have like common. For example, it should not have that a common husband or common wife. Okay, you should not have that. So very simple. So similar to matching, okay, and this is the application of matching. Application of matching, and this matching is a very important concept. Let me tell you, very, very, very important concept. This concept is used in economics. Okay, for stable matching, there is something called stable matching. For this stable matching, there is a problem called stable matching. For this stable matching, Nobel Prize has been awarded. Okay, for this problem, stable matching. You will study this problem in MTech. In algorithm course, you will study this problem. And for this problem, Nobel Prize has been awarded for this problem. The person who solved this problem, okay, the stable matching problem. Anyway, what I'm saying, this matching concept is basically very simple. You don't want common endpoints. Okay, this is the idea. Okay, you don't want all these must be different. All of them must be different. All of them. Okay, very simple. So tell me, what is perfect matching? What do you think from the marriage situation, from the marriage scenario? What is the perfect matching? See here, if you notice, M2 has no wife. So this is not a perfect matching, right? Yes or no? This is not a perfect world. Like M2 does not have a wife. Okay, yes or no? So basically, perfect matching means all the vertices must be covered. Okay, perfect matching means matching which covers all the vertices. Matching which covers all the vertices. Which covers all vertices, all the vertices. Okay, very simple. So matching which covers all the vertices must be covered. So very simple, this is the idea. Because here you can notice M2 is not covered. So this M2 is unmarried. I can say M2 has no wife. Okay, so if you notice, M2 has no wife. Okay, so this M2 has no wife. So that is the reason I can say this is not a perfect matching. Perfect matching basically means that this is a matching which covers all the vertices. This is the perfect matching. So tell me, in CN, okay, in CN, do we have perfect matching? When can you have perfect matching? Perfect matching. When do you have perfect matching? Perfect matching exists if and only if n is equal to, in CN, I am talking about CN. In CN, perfect matching exists when n is equal to even. When n is even in CN, I am talking about CN. Okay, so in this CN, the perfect matching will exist if and only if n is equal to even. For example, in this, there is no perfect matching. A, B, C. Here you don't have a perfect matching, because if you take, for example, if you take AC, now you cannot take something else. Okay, so the perfect matching does not exist. Whatever you do, perfect matching does not exist. So I can say perfect matching does not exist. Okay, this is the idea. Perfect matching. Let's call it, in short, let me call it PM. Okay, so perfect matching does not exist. PM, short. Okay, so this is the idea. And here the perfect matching will exist. So if you have C4 like A, B, C, D, now here the perfect matching will exist. You can take A, B, comma, C, D, and this is your perfect matching. Okay, so this is the idea. Let's take one more example to understand this matching concept. So tell me, if I have this graph, like complete graph. For complete graph, what do you think? What do you think for complete graph? What is the size? What is the matching number? For the complete graph, what is matching number? Matching number means size of largest matching. What is the for the complete graph on n vertices? What is the matching number? Matching number means size of largest. Size of largest. Think about it. Size of largest matching in a complete graph. Tell me. Think about it. For example, you have K1. You have K1. For example, you have K2. For example, you have K3. For example, you have K4. So tell me, here what is mu? What is the matching number? What is the matching number? Matching means size of edges. Matching number means basically largest matching. So here there is no edge. So the matching number will be 0. Here we don't have any edge. So the matching number here will be 0. Here what is matching number? 1, because you can take this edge. Here the matching number will be what? Here the matching number is also 1. Okay, here also matching number is 1. What about this case? Here matching number is what? That is 2. Here matching number is 2, because what you can do? You can take ABCD. You can take ABCD. Okay, so here matching number is actually 2, because you can take ABCD, something like this. Okay, see, very simple point. If you have Kn, Then because in Kn you have n vertices, you have 1, 2, 3, 4, and so on, total n vertices you have. Okay, these are your vertices. Tell me, are they adjacent to each other? All of them. This is a complete graph. So everyone is adjacent to another. Everyone is adjacent to another. So how will I make a matching? See, how will I make a maximum matching, largest matching? So let me create a largest matching. So how to create a largest matching? Because they are adjacent to each other. All of them are adjacent to each other. So how to create a largest matching? Very simple. Very simple. Forget about the graph. Just because every two are adjacent to each other. So like this, I can create the perfect match. I can create the largest matching. 1, 2, 3, 4, 5, 6, 7, 8, and so on. And so on. Okay. And so on I will create. So tell me now, did you understand that this will work as largest? This is your largest matching you can create, because all the elements are adjacent to each other. They are adjacent to each other. So I can say largest matching that you can create is like this. Okay, so quite simple. For example, if you have K5, in your K5 you have these vertices 1, 2, 3, 4, 5. So what will be the largest matching? What will be the largest matching? So the largest matching that you can create, that will be like this: 1, 2, 3, 4. Only this you can get. Only this you can get. And if you have K6, if you have K6, 1, 2, 3, 4, 5, 6, then what will be your largest matching that you can get? Largest matching you can get is like this. Okay, so here for K5, the matching number is what? The matching number is 2. For K6, matching number is 3. So finally, now tell me, what is the matching number of Kn? What is the matching number of Kn? The matching number, the size of largest matching that you can create, that is n by 2, again floor. Again, that will be n by 2 floor. Yes or no? Is it clear to everyone that this also will be n by 2 floor? Okay, so quite simple. So you can notice maximal matching, what that means. Maximal means, okay, maximal means you cannot add something more. Maximal means you cannot add something more. So for example, here, is this maximal matching? Is this maximal matching? Can you add something more? Can you add something more? Can you add one more age? You cannot add. So this is maximal matching. This is maximal, but this is not maximum. This is maximum. This is maximum. Is this perfect? Yes, this is perfect also. This is perfect also. Okay. And this is just a concept that vertex that appears in matching, that is called saturated. Like for example, in the marriage example, in your marriage example, this M3 is not our M2. M2 did not get a wife. So M2 is not saturated, something like that. So this is just a terminology. Okay. A vertex which appears in the matching is saturated. Otherwise, not saturated. Perfect matching means all vertices are saturated. Perfect matching means a matching in which all the vertices are present. Okay. So these are the quite simple things. What about bipartite graph? What do you think about bipartite graph? In a bipartite graph, K, M, N, what can you say? Perfect matching. How can you, okay, when perfect matching will exist? So perfect matching exists. When can you say perfect matching exists? In K, M, N. Perfect matching exists if and only if you have a complete bipartite graph. Just think about it. This is your complete bipartite graph. Tell me, in this K2, 3, perfect matching can exist if I have like 1, 2, A, B, C. Okay. So is it possible the perfect matching? Can perfect matching exist here in this graph? Can you create a perfect matching? Perfect matching means all the vertices must be covered. So here, what is the largest matching you can create? See the largest matching that you can create. See the largest matching. You can create, the largest matching that you can create is like this. Every edge will have one vertex from here, one vertex from here. Every edge will have one vertex from here, one vertex from here. So you, okay, so the largest matching you can create is like 1A, 2B. But this is not perfect. This matching is not perfect matching. So when can you create? So when can you create the perfect matching? The perfect matching exists if and only if M is equal to N. If both are same, then perfect matching will exist. For example, if you have K33, 1, 2, 3, A, B, C. If you have this, okay, K33, So this is your idea. This is the idea. Okay. K33. So here I can say this will be the perfect matching. I can take 1A, 2B, 3C. This is what I can take. Okay. So very simple. Is it clear to everyone? So in KMN, what is the largest matching number? In KMN, what is the matching number? What is the matching number? Mu. Mu means matching number. What is the matching number? Tell me. In KMN, the matching number. Matching number. That will be minimum of m comma n. That will be minimum of m comma n. Very simple. You can see from this example. Okay, so the matching number will be minimum of m comma n. Very simple. Okay, so this is the idea. So we have seen for complete graph. Now few interesting things about matching. You tell me, okay, and I will answer it. Like I will write the answer. The first question: how many vertices are saturated by any matching? Any matching, whatever matching you take, any matching will saturate how many vertices? Any matching covers how many vertices? Covers or saturates how many vertices? Saturates number of vertices. Number of vertices. Any matching, any matching, any matching. Array, any matching. I am asking, any matching will cover how many vertices? Whatever matching you take, it will cover how many vertices? It will cover even number of vertices. How can you give like any matching I'm talking about? Whatever matching you take, that will cover even number of vertices. For example, if you take this A, B, C, D, E, F. Okay. For example, if you have this one, now here you can notice any matching you take. If you take any matching, for example, this is a matching. Array, this is a matching, right? Yes or no? This is matching, correct? This is a matching. Similarly, you can notice AB comma EF. This is also matching. Okay, so like this is the idea. For example, CD, this is also matching. So how many vertices will be covered by any matching? What is the largest matching you can create here? In this, what is the largest matching you can create? So you can create like AB, CD, EF, AB, CD, EF. So this is your largest matching. So this is your perfect matching also. This is your perfect matching also. Okay, this is the perfect matching. So is this clear to everyone? That how many vertices a matching will cover? Any matching will cover how many vertices? It will cover even number of vertices. Any matching, whatever matching you take. Yes or no? Any matching you take, that will cover even number of vertices. From the marriage example, you can take, okay, just think from the marriage point of view. From the marriage point of view, like matching, like marriage point of view, man, women, marriage. So how many people will be covered by marriage? How many people will be covered by marriage? Even number of people. Okay, even number of people will be covered by marriage. So very simple. That is the same idea. See, when okay, remember this matching is basically you can think in terms of marriage. You can think in terms of marriage. Okay. So the second, this is your first question. Now the second question. Second question, tell me, can I say for any graph, it does not matter which graph, for any graph, can I say that matching number means largest matching that you can create, that will be less than equal to n by 2 floor. Is it true? Is this true? Largest matching that you can create. This is the largest matching that you can create. This is the largest matching, like size of largest matching. This is the size of largest matching. Okay, so can I say that for any graph, whatever graph you take, for every graph, I can say for every graph. So can we say that for every graph, this will happen? Why this statement is true? This statement is actually true. Yes, this statement is actually true. But why this statement is true? Tell me why this is true. Yes, because every edge will cover how many vertices? Exactly 2 vertices. Exactly 2 vertices. Every edge will cover exactly 2 vertices. In the matching, every edge will cover exactly 2 vertices, unique vertices. Every edge will cover exactly 2 unique vertices. Okay, so in matching, if you notice, in any matching, what will happen? Whatever matching you take, in any matching, this will happen. In any matching, every edge covers exactly two, okay, covers exactly two unique vertices, exactly two unique vertices. Okay, so this is the idea. So if you have any graph, then what is the, okay, so I don't know what is the graph. I don't know. I don't have any information about the graph. Let's assume this is your graph, G, V, comma, E. Okay, G, V, comma, E. I don't have any information about the graph. Let us assume you have these vertices, A1, A2, A3. These are your vertices, AN. Okay, then tell me, like I don't have any information about the graph. Then how can I say that the matching number will be definitely less than equal to n by 2 floor? Why? Because whatever happens, just think about it. Whatever happens, your worst case matching will be like this. Matching will be like this. For example, okay, in your matching, if you have, for example, if you have, let us assume that you have E1, you have E2, and let us assume you have EK. Let's assume this is your matching. Okay, E1 to EK. Let's assume this is your matching. Now, if this is the matching, then how many vertices are covered by this? How many vertices are covered? So this matching covers 2k vertices. So 2k vertices will be covered. Okay, this matching will cover 2k vertices. Very simple. Because this will cover two vertices, this will cover two vertices, and all these vertices are different. All these vertices are different. So I can say basically this will cover 2k vertices. Okay, so you can notice one thing, that in the, okay, what is the max, like what is the largest matching you can create? The largest matching you can create is, okay, that will have size less than equal to this. Because if you have size more than, okay, just think about it. If matching size, just think about it, if size of matching is greater than or equal to, okay, just think about it. Okay, like if this is greater than n by 2, then what will happen? If size of matching is greater than n by 2, means you have a matching, it means you have a matching whose size is, in this you have E1, E2, and so on, EK, where k is basically greater than n by 2. Then what it means? How many vertices are covered? Tell me. 2k. 2k means 2k vertices covered. Okay, 2k vertices covered. 2k vertices covered. And k is greater than n by 2. If you assume, like if you assume this, then k is greater than n by 2. It simply means that, okay, what it means? It means more than n vertices covered. It means more than n vertices covered. And that is not possible. And that is not possible. Okay, so that is not possible. Is this clear? So that is not possible. Okay, so is this clear to everyone? Please tell me. So whatever graph you have, whatever graph you have, the matching number will always be less than equal to this. The matching number is always going to be less than equal to this. And what can you, okay, so remember, for every graph, okay, so for every graph, what will happen? For every graph, I can say, for every graph G, I can say that matching number will be less than equal to n by 2 floor. And what can you say about age cover? What can you say about age cover? In the last class we have seen age cover. In the last class we have seen age cover number. That should be, in the last class we have seen age cover number. Age cover, that should be greater than or equal to this. We have already seen, right? Age cover number, beta dash. Beta dash means age. This is your age cover. This is your age covering number. This is the age covering number. Okay, so this will be greater than or equal to what? this will be definitely greater than equal to n by 2 floor or n by 2 seal, like we have seen in the last class. So this beta, n by 2 floor or n by 2 seal, I think it will be seal. See, you okay? See, if you are confused, just check it, because what should happen? It should cover all the vertices. It should cover all the vertices, right? It should cover all the vertices. See, just think like this. Just think like this. Please think like this. Very simple. You have edge cover. Okay, just think like this. Edge cover. Edge cover should cover all the vertices. Yes or no? It should cover all vertices. It should cover all vertices. It should cover all vertices. Now think about it. Total all vertices you have to cover. Now think about it. If your edge cover has E1, E2, and so on, EK, and let us assume that K is less than equal to, like K is, let us assume K is, I can say, if K is less than n by 2, if K is less than n by 2, okay, if K is less than n by 2, then what will happen? So this is your edge cover, and if K is less than n by 2, then what will happen? Remember, edge cover should cover all the edges. Now I am saying that if K is less than n by 2, then what will happen? If K is less than n by 2, then how many vertices are covered? In worst case, how many vertices are covered? If K is less than n by 2, then at most how many vertices are covered? 2k vertices, at most 2k vertices, at most 2k. Okay, I can say less than 2k basically. Okay, because then at most 2k vertices covered. At most 2k vertices covered. Vertices covered. And at most 2k vertices covered. What it means? It means how many vertices? Less than n vertices covered. It means less than n vertices covered. Okay, so that is the contradiction, and that is a contradiction. So this less than n vertices covered, and that is a contradiction. So actually this we have already seen. So what I'm saying that alpha should be less than equal to n by 2 floor, and beta dash, this edge covering number, this should be greater than equal to n by 2 seal. This concept, this we have already seen in the last class. I told you that every edge will cover, see, every edge will cover 2 vertices, but they need not be unique. Yes or no? In the matching and in the edge cover, what is the difference? See the difference between matching and edge cover. See the difference. A, B, C, D, A, B, C, D, E, F, G. So let's assume. So now notice the difference between matching and edge cover. What is the matching number for this graph? For this graph, what is the matching number for this graph? The matching number. The matching number is only one. Only one edge you can take for this graph. The one edge you can take. So the matching number is actually only one. You can take only one edge. You cannot take two edges. You can only take, for example, you can take BA, because whatever edge you take, A will be the common endpoint. Okay, and what is the edge cover? What is the edge cover? What is the edge cover number? Like what is beta dash for this graph? The beta dash will be 6. Okay, so edge cover, because edge cover should cover all the vertices. So the edge cover will cover all the vertices. For example, it will be AB, AC, AD, AE, okay, AG, AF. So like this. So you can notice one difference here. Actually, in the matching, okay, every edge will cover 2 vertices uniquely. Yes or no? In matching, every edge will cover 2 vertices uniquely. In edge cover, every edge will cover 2 vertices, but may not be uniquely. But uniquely is not required. So this is the difference. For this graph, mu is 1 and beta dash is 6. Okay, so this is the idea. Now tell me one more thing. Tell me one more thing. This is another question. If perfect matching exists, if perfect matching exists, then how many vertices should be there? then number of vertices should be what? Then number of vertices should be, if perfect matching exists, perfect matching exists means all the vertices are covered. Perfect matching means all the vertices are covered. If perfect matching exists, then number of vertices should be even. Should be okay. So the number of vertices should be, and the answer will be even. The number of vertices should be even, because if you are getting a perfect matching, the definition of perfect matching, what this says, perfect matching means it will cover all the vertices. Perfect matching will cover all the vertices. All the vertices must be covered. This perfect matching A1, A2 are like, for example, A1, B1, A2, B2, A3, B3, and so on. Okay, AK, BK. And remember, because it is perfect matching, so it covers all vertices. So it covers all vertices. All vertices. Okay, so if it is covering all the vertices, if this is covering all the vertices, it means these are all the vertices. What it means? What it means, if this is covering all the vertices, this is covering all the vertices, it means these are your vertices. This is your vertex set. This is your vertex set. So how many vertices are there? Number of vertices is basically nothing but, okay, all are different, right? Because this is a matching, because this is a perfect matching. This is a matching, this is a perfect matching. Okay, so all these are different. A1, B1, A2, B2, all are actually different. So I can say 2K, which is nothing but even. Which is nothing but even. Is this clear? The concept of matching, please tell me, is this clear? Like concept of matching, independent set, edge cover, vertex cover, all these concepts, are they clear? Anyone has any doubt? Let me know. Please let me know if you have any doubt. All these definitions, these are simple definitions. The definition of independent set. Independent means vertices are independent, means vertices are non-adjacent. Vertices are independent. Okay, so non-adjacent vertices. Click, click means complete subgraph. Okay, a subgraph which is complete. Largest click means a subgraph, the largest complete subgraph. Then we have seen vertex cover, means on the vertices you put security guard so that you can cover all the edges. Okay, you want to cover all the galleries. In the galleries you have paintings, okay, very expensive paintings, so you want to cover all the galleries, so you can put the security guard on the vertices. So that is your vertex cover. Vertex cover means vertices will cover all the edges. Okay, then we have edge cover. Edge cover means you put the security guard on the edges. Okay, like for example, many times at the night, okay, at the night the security guard will walk on the road, right? Yes or no? So like that. Okay, so you put the security guard on the edges so that it will cover all the vertices. So edge cover means edges which will cover all the vertices. Then we have seen matching. Matching means this is an edge independent set, means set of non-adjacent edges. Okay, this is similar to independent set. In the independent set we have vertices which are non-adjacent, and here in this matching we have edges which are non-adjacent. Okay, so we have done the complete analysis in the last two lectures. We have seen independent set, we have seen vertex cover, edge cover, we have seen many examples, we have seen all the complete analysis we have seen. Okay, and in this class we are learning this matching, the concept of matching, perfect matching, and matching number. So now this is the final point, that if you have a perfect matching exists, if perfect matching exists, it implies number of vertices even. It implies number of vertices even. Is this statement true? What about the reverse direction? What about the reverse direction? What about the reverse direction? The reverse direction. The reverse direction is not true. The reverse direction is definitely not true. Why this is not true? For example, this example you can take A, B, C, D, E. Take this example. Just take this example. So A, B, C. Number of vertices is even. You can notice number of vertices is even. Here, number of vertices is even. But do we have what is the largest matching? Do we have a perfect matching? Tell me, perfect matching exists? Here, can I say perfect matching will exist? Can you give me a perfect matching? No. There is no perfect matching. You cannot give me perfect matching. For this graph, what is the matching number? The matching number is 1. The largest matching you can create is only 1. Okay, so remember, if perfect matching exists, means there is a matching which covers all the vertices. So if perfect matching is existing, then it means number of vertices will be even. But if number of vertices is even, that does not mean that perfect matching will exist. We have already seen maximum matching. So we know that every perfect matching is maximum. Can I say every perfect matching is maximum? Can I say every perfect matching? Can I say every perfect matching is maximum? Yes, of course. And every maximum is maximal. Okay, but the reverse is not true. Every maximum is maximal, but the reverse is not true. This reverse is not true. Okay. So all these concepts we have seen, like matching. You can notice in matching what we have, the items are edges. In the matching, items are edges. This matching is a set of edges, such that at most one vertex per at most one edge per vertex. Next, anyway, so basically, like vertex cover, the item is vertices, at least one vertex per edge. Okay, so something like this. Okay, anyway, these are the definitions. You can just check them out. Now, so let's take a small break, and after the break, we will continue. So let's just take 8:40. Okay. Hi all, welcome back. Now let's see the relationship between matching and vertex cover. This relationship we need to study. What do you think? See, this is actually, these things are very simple. Let me tell you. All these things, all these relationships, these are actually very simple. In the last class, we have seen vertex cover and independent set, right? So for this vertex cover and independent set, we have seen this type of scenario. For example, if this is your independent set, then this will be your vertex cover. So this type of thing we have seen, right? Similarly, we have seen that if this is your vertex cover, then this will be your independent set. Okay. So this type of, this proof we have seen in the last class for vertex cover and independent set. This proof we have already seen. Okay. So similar proof you can do for this matching and vertex cover also. Like, okay, like just use the definitions, nothing else. So let's see. So this is the idea that cardinality of any matching, cardinality, remember, size of any matching, it does not need to be maximum matching. Okay, it does not need to be maximum matching. Cardinality of any matching, any matching, so size of any matching is less than or equal to, is less than or equal to size of any vertex cover, is less than equal to size of any vertex cover. So this is interesting. And how to prove it? How to prove it? See, this is the hint to prove. Take any matching of size k. You take any matching of size k, and what you prove? You prove that any vertex cover. I am not talking about minimum vertex cover. See, please, I am not talking about minimum vertex cover. I am not talking about maximum matching. I am saying any matching you take. So any matching you take of size k, then what you prove? You prove that every vertex cover must have size greater than equal to k. So how to prove this? This is very interesting, and this is like very simple also. So for example, if you have a matching, just think about it. Let us assume you have a matching. Let us assume you have a matching of size 3. Let us assume you have a matching of size 3. Matching of size 3. Okay, you take a matching. So there exists a matching of size 3. Let's assume. Okay. So if you have a matching of size 3, what it means? Tell me what it means. You have matching of size 3. What it means? It means you have these three edges. You have A, B, C, D, E, F. This is your matching, correct? This is your matching, right? Yes or no? Okay, let's assume you have a matching of size 3. So this is your matching. Now tell me one thing. Now tell me one thing. Any vertex cover, if I create any vertex cover, vertex cover should cover all the edges. Yes or no? It should cover all edges. All edges. It should cover all edges. Okay. EF, EF. Okay. EF. So A, B, C, D, E, F. Now, vertex cover should cover all the edges. If I need to cover all the edges, tell me, what can you guarantee? What can you guarantee? I need to cover all the edges. So tell me, okay, to cover this edge, E1, I have to take at least one of them, yes or no? Who can cover E1? Tell me. Who has the capacity to cover E1? Who has the capacity to cover E1? There can be other, remember, there can be other edges. Remember, there can be other edges, there can be other vertices, there can be other vertices, there can be other edges. So let us assume you have matching of size 3. This is your matching. In your graph, you can have other vertices. Remember, please remember, your graph can have other vertices, other edges. Your graph can have anything. Okay, your graph can have anything. Your graph can be anything. Your graph can have anything. Your graph can have anything. So this is your matching. Now tell me. So if you want to cover, because remember, vertex cover should cover all the edges. So if you want to cover this E1, then at least one of them you need. At least one of them you need, A or B. At least one of them you need. Okay, so if you want to cover E1, at least one of them you need. At least one of them you need, either A or B. Either A or B. To cover E2, these, remember, these 6 vertices are different or not? Can I say these 6 vertices are different? A, B, C, D, E, F. Are they different? Yes, they are different because it is a matching. Because it is a matching, so yes, they are different because it is a matching. So if I want to cover this word, this as E2, then I have to take C or D, at least one of them, at least one of them. And if I want to cover E3, then at least one of them I have to take, E or F. At least one of them I have to take. Remember, this can be anything extra. There can be extra, but at least vertex cover size must be at least 3. Is this proof clear? So if you have matching of size 3, then definitely your vertex cover should have size at least 3. Whatever vertex cover you take, whatever vertex cover you take, it should at least have size 3, at least. Okay, it can be more, but at least size 3 must be there. Is this clear? So similarly, if you have a matching, let's assume if you have a matching with size, let's assume you have a matching with size 2k. Let's assume you have matching with size 2k. For example, this is your matching. Let's assume A1, B1, A2, B2, and so on, AK, BK. So let's assume this is your matching. In your graph, you can have more vertices, other vertices, you can have other edges, you can have, okay, for example, this type of edges you can have, for example, this type of new vertices you can have. So your graph can have anything, but this is the matching that I'm taking. In your graph, you have this matching. This is your matching in your graph. Now tell me one thing. So this is your matching. This is a matching. I'm not saying that this is a maximum matching. This can be any matching. Okay, maximum or I don't care. Okay, maximum, perfect, not maximum, anything. This can be any matching. This can be single edge. I don't care. This is any matching. So you have a size, you have a matching of size 2k. Now tell me, what can you guarantee about vertex cover? What guarantee can you give about vertex cover? What guarantee? What guarantee you can give about any vertex cover? Remember, any vertex cover should cover all the edges. Remember, any vertex cover should cover all edges. You should cover all edges. So what guarantee you can give for vertex cover? This vertex cover should have at least, okay, so sorry, size k, matching of size k, sorry for that, matching of size k. Because remember, this is a matching of size k. Is this matching of size k or 2k? On your screen, this is matching of size k or 2k? This matching has size k or 2k? Matching means set of edges. So how many edges you have? Only k edges you have. Remember, matching means a set of edges. Matching means a set of edges. So how many edges you have? Total k edges you have. So this is matching of size k actually. This is the matching of size k. Now tell me, so what guarantee you can give? This vertex cover size must be at least k, because vertex cover should cover all the edges. All the edges must be covered. Who has the capacity to cover E1? To cover E1, you have to take A1 or B1. If you want to cover E2, you have to take A2 or B2. You have to take A2 or B2, and so on. If you want to cover EK, then you have to take AK or BK. Either you have to take AK or you have to take BK, or both. Or both. Either you have to take AK or BK or both. See, at least one of them you have to take. Maybe both. At least one of them you have to take, maybe both. At least one of them you have to take, maybe both. So for example, let's take example. Consider this graph. Consider this graph. Okay, A, B, C. Consider this graph. So let me give you a matching. Let me give you a match. Can anyone suggest a matching? Suggest any matching. Suggest a matching. This matching you can suggest. This matching you can suggest, right? This matching E1, E2, E3. So this matching E1 you can suggest. Okay. Now tell me, vertex cover. Remember, this is your matching. So what guarantee I can give? What guarantee I can give? What guarantee I can give? If I, okay, remember, vertex cover should cover all the edges. All the edges must be covered. So to cover E1, at least one of them I have to take. At least one of them I have to take. At least one of them I have to take. But is it enough? Did we cover all the edges? Did we cover all the edges? No. So take B also. Take B also. Now it is vertex cover. Are you getting my point? So at least one of them we have to take. I am not saying that exactly one of them. At least one of them. For example, here you can notice both of them we have to take. We have to take both of them. Is this clear? The point, the concept is clear. Another example you can take. For example, let me take this A, B, C, D, E. Consider this graph. Give me a matching. Give me a matching. So this matching you can give me. Actually, for this graph, the matching number is 1. So this matching you can give me. So what can you say about vertex cover? What can you say about vertex cover? Remember, this is your edge. To cover this edge, at least one of them we have to take. At least one of them we have to take. At least one of them we have to take. Okay. So let me take A. At least one of them we have to take. Let me take A. And this is enough. And that's it. This is enough. Now we have covered all the edges we have covered. Okay. So like this. Is this proof clear to everyone? What is happening here? So if you have any matching of size K, if you have any matching of size K, any matching of size K, then if you have any matching of size K, then what it means? Then what it means implies any matching of size K. If you have an if there exists a matching of size K, it means what? It means there exists a vertex. It means every vertex cover. See, if there exists a matching of size K, then for all vertex cover, every vertex cover must have size what? Then every vertex cover has size greater than equal to K. Okay. So this is the idea. If there exists a matching of size K, if there is any matching, there exists a matching of size K, then every vertex cover will have size greater than or equal to K. So this same point I can also say that the largest matching. Okay, this same point can I say like this? From this same point, can I say that the largest matching from here? Can I say that the matching number will be less than equal to vertex cover number? Can I say this? Can I say this? The maximum matching, because remember, any matching you take, then the vertex cover size must be greater than or equal to this. So I can say if you take maximum matching, then I can say that definitely this mu is less than equal to beta of G. This is point you can say. So this is the idea. Okay. The cardinality of any matching, whatever matching you take, the cardinality of any matching is less than or equal to the cardinality of any vertex cover. And this proof we have already seen. And the proof is very simple. Okay. So what is the proof? Just visualize in your mind. Forget about it. Okay. Don't read the slide. Okay. Just close your eyes and visualize. Close your eyes and visualize. You have a matching. You have a matching. There are edges. You have a matching. So vertex cover should cover all the edges. So who will cover these edges of the matching? You have a matching. Vertex cover should cover all the edges. So who will cover these edges of the matching? So to cover these edges of the matching, there are other edges also, but to cover these edges of the matching, you need at least one vertex from each edge. At least one vertex from each edge you need. At least one vertex from each edge of matching you need. So vertex cover size should be greater than or equal to matching size. Is this proof very clear? How many students have very clear idea of this proof? Okay, clear? So these type of things you have. These are very simple things. So the maximum matching and minimum vertex cover. The maximum matching and the minimum vertex cover. What is the relationship between them? We have already seen that this is the maximum matching. This is your maximum matching. This is the matching number. This is less than equal to minimum vertex cover. So what is this? This is the size of maximum matching. This is your size of maximum matching. So the size of maximum matching is basically less than equal to, and what is this? This is size of minimum vertex cover. This is size of minimum vertex cover. Okay, so the size of maximum matching will be less than equal to size of minimum vertex cover. There is one more interesting thing. This beta, actually this vertex cover number is less than equal to double of matching, double of maximum matching. This relation, how to prove this relation? This relation is saying that beta means this vertex cover number is less than equal to twice the maximum matching number. Okay, how to prove this? This is also very simple proof, If you have a maximum matching, okay, so this we have that vertex cover number should be less than equal to this. Yeah, okay. So if you have a maximum matching, so let us assume you have a maximum matching. Let's assume you have a maximum matching. Okay, so assume that this is the maximum matching. Just assume. Okay, for a moment, let us assume that this is your maximum matching. A, B, C, D, E, F. Let's assume that this is the maximum matching. Remember, this is the maximum matching. This is what I'm assuming. So let's assume. If this is the maximum matching, then tell me one thing. Okay, please tell me one thing. If this is the maximum matching, then is there any age? Which is like this, like which is not incident on these vertices? Can I say every age is incident on these vertices? And every age is incident on one of these vertices? Can I say? Can I say every age will be incident on one of these vertices? Tell me why. Okay, this type of age, is it possible? Is it possible this type of age in the graph? See, in the graph, you can have this age. In the graph, you can have this age. In the graph, you can have this age, this age, this age, this age. In the graph, you can have these ages. In the graph, you can have these ages. But tell me, is this age possible? Is this age possible? Why this is not possible? Why? What is the reason? Please tell me the reason. Abhipsa, Akash, what is the reason? Yes, because this is the maximum matching. Very good. Abhipsa, very good, very good. See, because I am assuming this is the maximum matching. If this is the maximum matching, this is the largest matching, it means this age cannot be there. If this age is there, then if this age is there, like if there are different vertices, let's assume x comma y, then if such age we have, then what I will do? If I have this age, then what I will do? Then there is a contradiction. There is a contradiction because if I have this age, then there is a contradiction because I can include here. There is a contradiction that this is maximum. There is a contradiction that this is maximum because I can use it here. I can use it here. Yes or no? So if I have this age, then I have a contradiction. So what I can say, if you have maximum matching, so this is the idea. Okay. So this is a note you can take. And this is very simple point that, okay, every age, okay, so if S is maximum matching, if S is maximum matching, then okay, this is a true false statement. Someone can ask you, like if S is maximum matching, F is maximum. If S is maximum matching, then I can say every age of the graph. Every age of the graph. Okay, every age of the graph. What I can say? Every age of the graph is incident on at least one of the vertices. Okay, is incident on some vertex. Is incident on some vertex covered by some vertex covered by S. Is this clear? Tell me. So if S is maximum matching, because remember, let's assume you have a graph. This is your graph G, V, comma, E. This is your graph. In this graph, let's assume S is maximum matching. This is your maximum matching. So if this is your maximum matching, then what I can say, because this S is maximum matching, this is your S, and this S is maximum matching. For example, A, B, C, D, E, F, G, H. Let's assume this is the maximum matching. If this is the maximum matching, then every edge of this graph, for this graph, every edge must incident on these vertices. Every edge must be incident on at least one of these vertices. Every edge must, for example, this type of edge also can be there, no problem. Okay, this type of edge can also be there. This type of edge can also be there. So this is possible. This is possible. This is also possible. Okay, this is also possible. This is also possible. But what is not possible? What is not possible? This type of, in G, this type of edge is not possible, like XY. This type of edge is not possible, because if you have this type of edge, then there is a contradiction, and the contradiction is that if you have this type of edge, then array include this in S and get a bigger matching. So there is a contradiction that S is a maximum matching. If you have this type of edge, it means S is not maximum matching. Okay, so I can, this is the idea. Okay, so I can say this type of edge, X comma Y, this type of edge not possible. This type of edge not possible. So very simple. So this is the statement. This is the theorem. This statement can come as true or false statement. Okay, tell me one more thing. See, the proof is not important in the GATE exam. The proof is really not important. Like, no one will ask you the proof. But still, one thing you remember, the proof is not important. They will not ask you the proof, but they can ask you these small points which are from the proof. These small points they can ask you as a true false. For example, this question can come as a true false statement. There will be 4 options. One option will be like this. So, okay, so take care. Is this clear to everyone? So understand everything. Is this point clear? Is this statement clear? If S is maximum matching, then every edge of the graph is incident on some vertex covered by S. Every edge is basically every edge. Okay, so finally, if this is the situation, then what can I say? It means these vertices are covering all the edges. Can I say it means these vertices are covering all the edges? Okay, so from here I can say, that S, vertices of S, I can say vertices, okay, vertices covered by S. So I can say vertices covered by S will cover all edges, isn't it? Will cover all edges. Yes or no? Because already you know that every edge is falling on these vertices which are covered by S. Every edge is falling on these vertices which are covered by S. It means what? It means that vertices covered by S, these vertices which are covered by S, they are basically, they will cover these vertices which are covered by S. These vertices will cover all the edges. So I can say these vertices covered by S, what can I name them? What can I call them? Vertices covered by S. What can I call them? Covered by S is, so vertices covered by S is what? So vertices covered by S is vertex cover. Yes or no? Is vertex cover, because it is covering all the edges. So it is vertex cover. Okay, so this is the idea. Very simple. So this is the proof also. So finally I can say that these vertices is definitely a vertex cover. So I can guarantee that this is my vertex cover. I can guarantee that this will be my vertex cover. If I take all these vertices, okay, if I take all these vertices A, B, C, D, E, F, then I will definitely get a vertex cover. Okay, so this will definitely be a vertex cover. If this is a vertex cover, then what is the minimum vertex cover? Tell me. What is the size of this vertex cover? Please tell me. What is the size of this vertex cover? Size of this vertex cover. Size of this vertex cover. That is 2 of mu G. That is 2 mu. That is 2 mu. Yes or no? 2 mu. 2 into mu, because this is the number, this is the size of matching, means mu, size of maximum matching. So I can say this is the, now this is a vertex cover. Then what can you say about minimum vertex cover? Then if this is the vertex cover, this is a vertex cover, but I am not saying this is minimum. This is a vertex cover. I did not say that this is minimum. This is a vertex cover. So what can you say about minimum vertex cover? That is less than equal to 2 mu. Is this clear? If this is vertex cover, then the minimum vertex cover should be less than equal to this. Yes or no? If this is the vertex cover, then minimum vertex cover should be less than equal to this. And this is the idea. Did you understand this statement? This is also a GATE exam question. This is also a GATE exam question. Did you understand? Very simple. See, okay, so mu is less than equal to vertex cover is less than equal to 2 mu. So quite simple. For which graph? These, for example, if you take these graphs, like, okay, for which graph, this is my question. For which graph this will happen? For which graph mu will be equal to beta? For which graph this will happen? Mu will be equal to beta. Can anyone tell me? For which graph? Give me a graph. Give me a graph. Okay, for which graph? Like, give one graph, I can say. Give one graph for which, give some graph. Okay, with, give some graph with this mu is equal to beta. Give some graph with mu equal to beta. So can anyone give me some graph where mu is equal to beta? Complete graph. No, 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 no. Complete graph is not correct. Complete graph is not correct. Cn with even vertices. Yes, this will work. Cn with even vertices. This will work. A, B, C, D. So here you can notice mu will be 2 and beta is also 2. Okay. So if you notice C even, if you notice C even, then you can notice that mu is also n by 2. Okay. Mu is also n by 2 and beta is also n by 2. So both are actually same. Complete graph is will not work. Remember, complete graph will not work because if you have complete graph, then for complete graph, what is the vertex cover? For complete graph, what is the vertex cover? The vertex cover is n minus 1. For the complete graph, the vertex cover is n minus 1. We have already seen in the last class. And what is the mu? What is the mu? Mu is n by 2. N by 2 floor. This will be the mu. Okay. So like this you can say. And complete bipartite graph. What can you say about complete bipartite graph? KMN. For this complete bipartite graph, mu we have already seen. Mu is minimum of m comma n. Okay. So tell me what is beta? What is the vertex cover? The vertex cover for this vertex cover, that will also be minimum of m comma n. That also will be minimum of m comma n, right? Vertex cover, because if you have this graph like km comma n, for example k2 comma 4 you have. Okay, let's assume you have k2 comma 4. Then vertex cover means which will cover all the edges. So this will cover all the edges. This will cover all the edges. Covers all edges. This will cover all edges. So I can say that okay, so I can say beta will be equal to 2. So this is the idea. So for kmn also these will be same, but for complete graph this will not happen, and for cycle graph C even this will happen, and for C odd, for C odd this will not happen. You can just check. Okay, now for which graph this will happen, like beta is equal to 2 mu. For which graph this will happen? Beta is equal to 2 mu. Give a graph. Give graph with this feature, beta equal to 2 mu. Yes, odd cycle. You can give odd cycle. You can give C3. You can give C5. So you can create C3, C5. You can create, or you can create complete. So okay, so C3, C5 you can create. You can also create K5, K7. You can also create them. You can also create complete graph on odd vertices. Basically you can create C odd, or you can create K odd. You can create C odd, you can create K odd. For example, if you have C odd, then what will be beta? For C odd, what will be beta? Beta means vertex cover. So what will be vertex cover? That will be n by 2 seal. The vertex cover will be n by 2 seal, and the mu will be what? When you have C odd, so vertex cover. Okay, so mu will be what? Mu will be n by 2 floor. Mu will be n by 2 floor. So I want beta equal to 2 mu. This is what I want. Beta equal to 2 mu. Will it happen here? Will it happen here? Like for C3, it is fine. For C5, will it happen this? This will not happen for C5, right? So this will, okay, so for C3 this will happen, but for C5 this will not happen. Okay, so this is wrong. This is wrong. So for C5 this will not happen. Basically I can say K3, K4, K3, K5, these you can take. You can take K3, K5 and so on. Okay, so this C odd will not work. This C odd will not work. Okay, this will not work, but K odd will work. K odd will work. The beta K odd will be n minus 1. The beta will be n minus 1, and the mu will be n by 2 floor. Okay, the mu will be n by 2 floor. So this will happen. Okay, here it will happen. For C5, what is the, tell me, for C5 what is beta? For C5 beta is 3. And what is mu for C5? For C5 mu is 2. So clearly beta is not equal to 2 mu. You can notice beta is not equal to 2 mu. I am asking for this. This will always happen. Arpan, this will always happen. For every graph, this will happen. So for that, you don't have to apply your brain. For every graph, this will happen. For every graph, beta will, this will always happen. This will always happen. For this, you don't have to apply your brain. I am asking when they will be equal. See, this will always happen. For every graph, this will happen. So here you don't have to apply the brain. I am asking when they will be same, when they will be equal. This is what I am asking. So they will happen when you have k equal to odd. For k equal to odd, this will happen. Okay. So very simple. So all these points we have seen. All the points. And this is just a for bipartite graph. This proof we will not see, and this is not required for GATE exam. This theorem is not required for the GATE exam, but sometimes what happens, this theorem is so popular. This is very popular. So because this is very popular, so sometimes in some poor test series, there you can find it, and then you will come to me and then you will say, sir, you did not teach this. See, this theorem is beyond the, I can say, beyond GATE level. This theorem is beyond GATE level, but this is very popular. Let me tell you, this is extremely popular theorem. So just this statement, we will not see the proof, but you can understand, but you can remember this statement. So this is for bipartite graphs. This theorem is for bipartite graphs. So this is only for bipartite graph. This theorem, what this is saying? This theorem, what this is saying? This theorem is saying what? This theorem is saying that if you have bipartite graph, then maximum size of matching is equal to minimum size of vertex cover. See, for any graph, what will happen? For every graph, what will happen? Like whatever graph you take, for every graph, what will happen? Whatever graph you take, for every graph, what will happen? Mu will be less than equal to beta. This will happen. Mu will be less than equal to beta, and this will be less than equal to 2 mu. So this will happen. But for bipartite graph, what will happen? For bipartite graph, what will happen? For bipartite graph, mu will be equal to beta. Okay, this is the simple point. This is what I'm saying. For bipartite graph, they will become same. They will become equal. Okay, so for bipartite graph, they will become equal. For every graph, this will happen. Whatever graph you see, this proof we have already seen. For this statement, the proof we have already seen. But for bipartite graph, this will happen, that mu will be equal to G. Mu will be equal to G. This will happen for bipartite graph. And this is known as Koenig theorem. This statement for bipartite graph, they will be same. This is known as Koenig theorem. Koenig's theorem. Okay. Is this clear? The statement, is this clear? The statement. This we have already seen. For every graph, this will happen. This we have already seen, that this matching number will be less than equal to beta. Beta will be less than equal to 2 mu. This we have already seen for every graph. For bipartite graph, what will happen? For bipartite graph, they will be same. But remember, this is just a this is a, I can say, this is only one way theorem. This is only one way theorem. So if you have bipartite graph, then this will happen. But if this is happening, it does not mean you have a bipartite graph. Is this clear? So if you have a bipartite graph, if you have a bipartite graph, then what will happen? If you have a bipartite graph, then mu will be equal to beta. But remember, mu equal to beta does not mean bipartite graph. For example, okay, you can take mu equal to beta does not mean bipartite graph. So for example, take this complete graph on 4 vertices. Take this K4. For this K4, what is mu? Mu is 2. What is beta? Beta is 2. Okay, but this K4, this has odd cycle, so this is not bipartite. Yes or no? This has odd cycle. This K4 has odd cycle, odd length cycle. So this K4 has odd length cycle, so this is not bipartite because it has odd length cycle. This is your odd length cycle. Okay, so this is the idea. So this is one way theorem. So if your graph is bipartite, then matching number will be same as covering number. But if they are same, it does not mean that this is bipartite. For complete graph, we have already seen that vertex cover will be n-1 and maximum matching will be n/2 floor. This we have already seen. Okay, so all these concepts we have seen. Every concept we have seen. Okay, so did you understand? This is your all the concepts we have seen: edge cover, vertex cover, independent set, matching. All the 4 concepts we have seen. There are many questions in, not many, but I think there are 5 or 6 questions in the GATE exam from these concepts, and the latest question is in 2022 from these concepts. There are 5 or 6 questions. Okay, but these concepts are very important in graph theory. And let me tell you one thing. See, whenever some concept is very important, then someday that question will definitely come in the GATE exam. They will make it easy. Okay, for example, some concept is very important. Let's assume, for example, I can say like matching. The concept of matching is very important. Okay, so someday they will definitely ask a question on matching in the GATE exam. They will ask an easy question, but they will definitely ask. Okay, is this clear? So how many of you can say that you understood all of it, like all of them? See, proofs are very simple. All the proof that we have seen, these are very simple. Yes or no? Every proof that we have seen, that is very simple. Did you understand the proofs? All the proof that we have seen, did you understand them? Okay, so let's see for this graph. Let's see for this graph, what is the matching? What is the matching number? Like A, B, C, D, E, F. What is the matching number for this graph? What is the mu of A? For this graph, mu. For this graph, what is mu? Matching number. Matching number will be what? So the largest matching you can create is like AB. You can take AB, you can take DC, you can take EF. So the matching number will be 3 and perfect matching exists. So here actually perfect matching exists. There is a perfect matching. Okay. So the mu will be equal to 3. And there is a perfect matching. You have a perfect matching. Okay. So this is the idea. And what is the edge cover for this graph? What is the edge cover number? Like beta dash. What is the edge cover? If you want to cover all the by using edges, you want to cover all the vertices. Minimum number of edges you want to use, and you want to cover all the vertices. All the vertices you want to cover. If you want to cover all the vertices, then what I need to do? Remember, this is this we have already seen in the last class. This is this is the wheel graph. This is the wheel graph, and we have already seen the wheel graph in the last class. So you want to cover all the vertices you want to cover. Then what you can do? You can do AB, you can do AB, you can do EF. Okay, you can do AB, EF, and you can do CD. So again, you can notice that this beta dash also will be 3. This beta dash is also 3 because you want to cover all the Okay. Arpan is saying this is example of conic. Are, is this bipartite graph, Arpan? Is this bipartite graph? This is not bipartite graph because this is not bipartite graph because this is not bipartite graph because there is a odd cycle. There is a odd cycle. This is not bipartite because there is a odd cycle. And what conic theorem says? What conic theorem says? Conic theorem says that if your graph is bipartite, then matching will be equal to vertex cover, not edge cover. That is vertex cover, not edge cover. This is your edge cover. This is the edge cover number. This is the edge cover number. This is the edge cover number. And the conic theorem says that if your graph is bipartite, then this is your vertex cover number. This beta is your vertex cover number. And this is your matching number. Okay. So like this. So for this graph, edge cover will be 3. This mu will be 3. And for this graph, what will be the beta? Vertex cover. Vertex cover, which will cover all the edges. You want to cover all the edges. You want to cover all the edges. So vertex cover. So you can take B. This will cover these edges. See, if you take D, vertex cover, vertex cover, vertex cover. So if you take D, then it will cover all these edges. So now these edges are gone. These edges you have covered. Then you can take AE, AEF. Then you can take AEF. So the vertex cover number will be 4 actually. The beta will be 4. So if beta is 4, then what is alpha? 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 So you can notice that beta is 4. So then alpha independent set, alpha. So here you have 6. So that will be 2. Alpha will be 2. Can you notice what is the largest independent set you can create? What is the largest? Can you take D? If you want to create largest independent set, can you take D? To create, you want to create largest independent set, can you take D? If you take D, you cannot take anything else. If you take D, you cannot take anything else. So you cannot take D. If you want to create largest independent set, you cannot take D, because if you take D, you cannot take anything else. So finally, I can take A, E. So anyway, you can notice beta is 4, alpha is 2. Because we already know that alpha plus beta is equal to N. This we already know. Independent set vertex cover, that is equal to N. For this graph, all the data, this is your C6. For this C6, what are all the data? Tell me. First, you tell me alpha. Independent set, that will be 3. Independent set. Vertex cover, what is the vertex cover? That also will be 3. What is the edge cover? You want to cover all the vertices. What is the edge cover? That also will be 3. And what is the matching? And what is the matching? That also will be 3. So for this C6, all things will be actually 3. All these things will be 3. Okay, let's see for this graph. So like this, for this graph, you tell me, first you tell me for this G2. Okay, find all of them. So what is alpha? What is beta? What is alpha dash? And what is beta dash? Tell me what is alpha dash? Alpha dash is same as mu. Remember, these are same symbols. So what is, okay, for this graph, you tell me what is alpha. For this graph, what is the independent set? The largest independent set that you can create. So you can take this vertex, this vertex, this vertex. These are you can take. So finally, the largest independent set, okay, so this is, if alpha is 3, then what is beta? If alpha is 3, then what is beta? So there are 6 vertices. So the beta also will be 3. Okay, next, what is mu? Matching number. Matching number. You can take this edge, you can take this edge, you can take this edge. So the matching number will be 3. Okay, and what is beta dash? Beta dash means edge cover number. What is edge cover number? edge cover number, that also will be 3. How many edges you need? So for example, you need this edge, you need this edge. If you want to cover all the vertices, we want to cover all the vertices, so you need 3 edges. Okay, so these are the parameters. And what about for this? For this, what is alpha? For this graph, can you take this vertex? If you want to create largest independent set, you want to create largest independent set, can you take this vertex? You cannot take this vertex, because if you take this vertex, you cannot take anything else. If you take this vertex, so finally I can say you cannot take this vertex. So what is the largest independent set you can create? You can take this, you can take this, then you can take this. So finally I think you will create only 3. So I think alpha will be 3. And what is beta? What is beta? If alpha is 3, then what is beta? If alpha is 3, then what will be beta? That automatically will be 4. Okay. And what will be matching? What is the matching number? The matching number, remember one thing, matching number is always less than equal to n by 2. Okay, so you have 7. So basically matching number will always be less than equal to 7 by 2 floor. So matching number will be less than equal to 3. So what is the matching you can create? So matching number will be 3, because you can take this edge. So basically you can take u1 u6, you can take u1 u6, you can take this, and you can take this. Okay, so matching number will be 3. And what is beta dash? Beta dash, edge cover. Okay, edges which will cover all the vertices. We want to cover all the vertices, so that will be 4. Okay. And for this graph, just quickly tell me, for this graph, what will be alpha, what will be beta, what will be alpha dash? Alpha dash means mu. And what will be beta dash? All these things you quickly tell me for this graph. First, what is alpha? Alpha means independent set. What is the largest independent set you can create? This is the independence number, stability number. Stability number means size of largest independent set. So what is the largest independent set you can create? From this, how many you will take? Tell me, from these 3, how many you can take? From these 3, you can take only 1. From these 3, you can take only 1. So what I can do? I can take this, I can take this, I can take this. This is what I can do. V1, V3, V5. Okay. So this alpha will be 3. Alpha will be 3. I will take V1, V2. So basically this, okay. So this will be like V1 I can take, V3 I can take, V5 I can take. Okay. If alpha is already 3, then what is beta? Beta is already n minus alpha. So that will be total, you have 1, 2, okay, total 5. So 5 minus 3, that will be 2. So 2. Tell me which 2 vertices are enough to cover all the edges? Which 2 vertices are enough to cover all the edges? Which 2 vertices? Which 2 vertices are enough? So you can take V2, V4. These 2 vertices will cover all the edges. These 2 vertices, they are covering all the edges. Okay. Next, what is matching? What is the largest matching you can create? So you can take, for example, you can take this edge, you can take this edge. So the largest matching you can create is 2. And what is the edge cover? What is the edge cover? You want to cover all the vertices. So you have to take this, you have to take this. Okay, then you have to take one of them. So finally it will be 3. So far what we have seen, okay, so far this is the conclusion, or I can say summary. This is the conclusion or summary. Let me tell you the summary so far. First, we have seen that this is the summary so far. So you have a graph where you have G, V, comma, E. This is your graph. Then this is the summary, that first point. What is the first point? That alpha plus beta. Okay, so let me just write here. First of all, let me write what are these things. Like, first of all, let me write what is alpha. So tell me what is alpha? Alpha is independence number. Independence number. This is the size of largest independent set. Okay, so this alpha is basically the size of largest independent set. Size of, okay, largest independent set. So that you already know. Okay, size of largest independent set. Many times I have told you. So this is your independence number. What is beta? This is your vertex cover number. This is the vertex cover number, means size of minimum vertex cover. This is the size of minimum vertex cover. Then what is mu? What is mu? This is the matching. This is the matching number. Size of largest matching. Size of largest matching. And what is beta dash? This is edge cover number. This is edge cover number. Size of, okay, minimum edge cover. So here what we want? Here what we want? Tell me. Here we want max or min? Here we want max or min? Max. Here we want min. Here we want max. Here we want min. Okay. So just give me 2 seconds. Just give me 2 minutes. Can you prove this? And this is very easy to prove. So just try this. And this is actually very easy to prove. Once I prove it, you will see that this is very easy to prove. So try this. Please try. Take a copy pen and think about it. Alpha means independent set. So the size of this independence number, the largest independent set, that is less than equal to edge cover. Okay, so try this. So did you try this? For any graph G with a delta, why this condition? Can anyone tell me? What do you think? Why this condition? This condition, why this condition? Delta means minimum degree greater than 0. To define, because remember this is independence number and this is your edge cover. Okay, so this is your independence number. This is the, I can say this is the independence number. This is the largest independent set. This is your largest independent set size. And this is the minimum. This is the minimum edge cover size. So this condition we have so that we can define, okay, so that we can define to define edge cover, so that we can define edge cover. Okay, so this condition we have so that we can define edge cover. Else edge covering will not be defined. In this case, only in this case edge cover is defined. So this is okay to define edge cover. Now tell me, can you prove it that largest independent set means independence number is less than equal to minimum edge cover size? Means, okay, so this is less than equal to edge cover. See, the idea is very simple. Just observe these two things. See, idea is very simple. Observe these two things. Observe these two things. So if you have independent set, just think about it. Okay, if I give you this largest independent set, you have a graph G, V, comma, E, and in this graph, let's assume you have a largest independent set. So let's assume this is your largest. Remember, this is the largest independent set, and this largest independent set is like this. Okay, this is your largest independent set. Here, let us assume that this is the largest independent set, A, B, C, D. Now, what it means? If this is the let's just assume that this is the largest independent set. If this is the largest independent set and edge cover, what edge cover will do? Tell me what edge cover will do. It should cover all the vertices. It should cover all vertices. Yes or no? Agree? Edge cover should cover all the vertices. It should cover all the vertices. So this edge cover should cover all the vertices. So tell me one thing. any edge, like, okay, tell me one thing. You want to cover all the vertices. For these 4 vertices, how many edges you need at least? You want to cover all the vertices. All vertices you need to cover. For these vertices, at least how many edges you need? For these vertices, if you want to cover these vertices, at least how many edges you need? Array, 4. 4, because this is independent set. Yuvraj, this is independent set. So there is no edge which can cover 2 of them. We don't have any edge. There is no edge which can cover 2 of them. This is independent set. This is independent set means there is no edge which can cover 2 of them. There is no edge which is incident on 2 of them because they are non-adjacent. They are non-adjacent. There is no edge here. You don't have any edge here. So there is no edge which can cover more than one of them. More than one of them. So tell me, edge cover want to cover all the vertices. You want to cover all the vertices. So if you want to cover all the vertices, then tell me how many, for to cover these vertices, how many edges you need? So at least 4 edges you need, yes or no? E1, E2, E3, E4. At least 4 edges you need, yes or no? At least 4 edges you need. This you need for A, this you need for B, this you need for C, and this you need for D. Is this clear? Isn't it simple? This statement, this proof, isn't it simple? So if you have a largest independent set, for example, this is, let's assume this is your largest independent set. If this is the largest independent set, what it means? It means there is no edge here. It means there is no edge. It means there is no edge here. You don't have any edge between them. Okay. So because there is no edge, so there is no edge which can cover more than one of them. So if you want to cover these vertices, then you definitely need at least 4 edges. If you want to cover this vertex, then you need a different edge. This vertex, different edge. This vertex, different edge. So for these 4 vertices, at least 4 edges you need. So finally, what I can say, so this is the proof. Okay, so this is the proof. So finally, this will be the proof is basically this. Is this proof clear? Very simple proof. Very simple. That alpha is less than equal to beta dex. So what was the summary? So you can notice independence number and all these things we have seen. So this is the summary. The first summary is alpha plus beta. This is equal to what? This is equal to number of vertices. Alpha plus beta is equal to number of vertices. Okay. Next, the second summary is the second relation that we have seen. What is the relation that we have seen? The second, I think this, that beta is greater than equal to matching number, and that is less than equal to twice the matching number. Okay. The third thing that we have seen is beta dash is greater than or equal to n by 2 seal. Beta dash is greater than or equal to n by 2 seal. This we have seen for all graph. These things will happen for all the graphs. And what is the fourth? Okay, so if your graph is G, V, E, then what is the fourth thing? This matching number, this is less than equal to n by 2 floor. Next thing, what is the next thing? Okay, so these things we have seen, 3, 4. Is there any other? I think these are right. Okay, and we have also seen this. Alpha is less than equal to what? Beta dash. This we have seen just now. Alpha is less than equal to beta dash. Okay. And also what we have seen? We have seen Koenig's theorem. We have seen Koenig's theorem, we have seen. So if your graph is bipartite, then what it means? It means mu is equal to beta. It means matching number is equal to beta if your graph is bipartite. Okay. So this is the idea. So actually this Koenig theorem, using this Koenig theorem, okay, so this if your graph is bipartite, this will happen. Let me tell you one more thing. Let me tell you just one more thing. You already know that alpha plus beta is equal to n, right? Yes or no? You already know that alpha plus beta is equal to number of vertices, right? This we have already seen, the proof we have seen. This is the most like cutest proof, very cute proof, very cute proof you have. Like if this is your independent set, then this is your vertex cover. So this is your very cute, like this proof we have already seen in the last class. Okay, yes or no? Actually, similar thing you can say for alpha dash plus beta dash. That is also equal to n. But the proof we will not see. The proof is hard. The proof is complicated. But okay, but you can notice both are actually similar. So these two statements are true. So alpha dash plus beta dash is also. What is alpha dash? What is alpha dash? What is alpha dash? This is your matching number. What is alpha dash? This is your matching number. Matching number means mu. This is your mu. Okay. And this beta dash is your edge cover. So this is the idea. Okay, so this is the complete explanation. Oh, this is the summary. We have also seen the summary. Is this summary clear? These things will help you. These things will help you. This will help you. This will help you. These things will help you a lot. Like this edge cover is greater than equal to n by 2 seal. And this matching number is less than equal to n by 2 floor. These things will help you a lot. This conics theorem will also help you. This conics theorem will also help you. This side is not true. Okay. Next, actually using this conics theorem, can you say for our let me ask you for hypercube graph. Let's see for hypercube graph. Hypercube graph Qn. For this hypercube graph, you tell me what is vertex cover? What is vertex cover? What is matching number? What is that? For hypercube graph. What is vertex cover? What is matching number? What is alpha? And what is beta dash? And what is beta dash? Remember? Remember. This hypercube graph is what? This hypercube graph is what? This we have already seen. This is what? This is a bipartite graph. This is a bipartite graph. This we have already seen. This is a bipartite graph. This hypercube graph. This is a bipartite graph. You already know the even parity, odd parity. The even parity, odd parity. This we have already seen. Okay. So this is your bipartite graph. And because this is bipartite graph, so what should happen? Because this is bipartite graph, so mu is equal to beta. So mu will be equal to beta. This matching number will be equal to beta. And what is the matching number? Remember, half vertices are here and half vertices are here. Okay, so what is the matching number? The matching number, what will be the matching number? The matching number will be half vertices are here, half vertices are here. For example, 2 power n minus 1 vertices are here, 2 power n minus 1 vertices are here. So the matching, so the matching number will be like this. You can create this type of matching, you can create. Okay, so like this you can create the matching. And okay, what is the vertex cover? What can I say about vertex cover? Because so this will be the vertex cover, yes or no? This will be the vertex cover. So I can say, if you, for example, this will be your vertex cover, I can say this will be the vertex cover. So finally here I can say 2 power n minus 1, because both will be same. Or you can create this type of matching, you can create this type of matching, you can create. Okay, so this is the idea. And for Qn, what else you can say? For Qn, what is the independent set? What is the independent set? That is also 2 power n minus 1. This will be your independent set. This will be the independent set. This will be the independent set, because there is no edge here. You don't have any edge here. And if you have alpha, then beta will be number of vertices minus alpha. So that will be 2 power n minus 2 power n minus 1. That is also 2 power n minus 1. Okay. So like this you can do. So all these things we have already seen, very simple. If anyone has any doubt, this is what we have to by heart. I told you, okay, proof complicated. Okay, so this is like we already know. So this is actually, we know that alpha plus beta is equal to, this we already know, alpha plus beta is equal to number of vertices is equal to n. Similarly, okay, similarly, this is similarly. The proof you can skip. But these are actually simple because you already know this. So automatically you can understand this also. Okay, so this is our topic and this is the complete analysis and we have already seen. For this question, just quickly answer it. Remember in this question, matching means perfect matching. Basically this matching word, this matching word, this matching word, that basically means perfect matching. So replace this matching with perfect matching. So actually this should be perfect matching. This should be perfect matching. Similarly here, this should be perfect matching. Okay, this should be perfect matching. Anyway, so tell me, for which n complete graph will have perfect matching? For which n complete graph will have perfect matching? For which value of n? So you can notice that this kn has perfect matching. This has perfect matching. So when this will have perfect matching? If and only if n is even. Very simple. If and only if n is even. If your n is even, then it will have a perfect matching. If and only if n is even. Prove that if graph has matching, then number of vertices will be even. If graph has a perfect matching, this we have already seen. See, this matching, basically this should be perfect matching. Here you must have perfect matching. Okay, so this we have already seen that if you have perfect matching, if your perfect matching exists, if perfect matching exists, then number of vertices will be even. We have already seen, but number of vertices even does not imply perfect matching. This we already know. Next, is the converse true? No, the converse is not true. For option C, the converse is not true. You can take, for example, A, B, C, D. This example you can take. Here you can notice number of vertices is even, but perfect matching does not exist. Okay. So this question was just, you can try. Okay. Anyway, so this is enough. So we have seen all these concepts. Tomorrow we will start. Tomorrow our topic will be, tomorrow we will start another topic, that is chromatic number, coloring. Coloring we will study tomorrow. Okay. So if anyone has any doubt, you can ask. Please don't keep any doubt. Whatever doubt you have, you ask. Any doubt? Anyone? Hello, Arpan?
Yes, sir. I had a small doubt in the edge cover. So there was a figured in page 120. Can you just go back to that? I had a doubt how the edge cover is happening over there.
How the
How the edge
edge
cover is
covering?
happening over there.
Which question?
So I think it was in 120 page or something like that.
This question?
No, sir. Like the previous one, I guess.
This question?
Yes, yes, yes. This one or the left one. How are you getting the edge cover as 4? Can you just repeat that?
How we are getting edge cover? Because edge cover means you should cover all the vertices. You must cover all the vertices. Okay, so let's try to cover all the vertices. Total 7 vertices you have. Okay, if you want to cover 7 vertices, how many edges you need?
So it has to be.
We already know that beta dash is always greater than equal to n by 2 ceil. This we
Yes.
already know. For every graph, this will happen. For every graph, this will happen, that beta dash will be greater than equal to n by 2 ceil. Here, so here also beta dash, will be greater than equal to 7 by 2 ceil. Okay, here also beta dash will be greater than equal to 7 by 2 ceil. That means beta dash will be greater than equal to 4. It means beta dash will be greater than equal to 4. Now all you have to do, just check using 4 can you do. See, beta dash will be greater than equal to 4. Now what you have to check? Beta dash cannot be less than 4. Beta dash will be greater than equal to 4. Now all you have to check, what you have to check now? Can anyone tell me what you have to check? So you have to check, do we have 4? Like, can we cover using 4? Can we cover using 4 edges? So very easily you can cover using 4 edges. You can take this edge, you can take this edge, you can take this edge, and you can take this edge. So 4 edges are enough to cover all the vertices. Is this clear?
So edge cover, it can have common edge, like it can share, it can.
Beta dash means minimum size of edge cover. Size of minimum edge cover. That is the
Oh
beta
yes,
dash.
yes. That was yes. I got confused. Like in the latter half, it is sharing one vertex. So I got confused in that.
It
Okay.
does not matter, they can share. That is, this is not matching. We are not talking about matching. We are talking about edge cover. Edge cover means edges which will cover all the vertices. We only want to cover all the vertices. We don't care about repetition and all. We want to cover all the vertices. So you can notice that here you can cover all the vertices. These 4 edges that I have created, these 4 edges will cover all the vertices. Okay, so the answer will be beta dash will be equal to 4.
And so
Okay,
whenever we are talking about beta dash, it has to be minimum edge cover, right? Like because like we can go above 4 if we wanted to.
yes, that is the
So
idea. Beta
exactly.
dash, what is this beta dash? This beta dash is, what is this beta dash? Can you tell me? This beta dash is size of minimum edge cover. This is the
Exactly.
size of minimum edge cover. This is the definition of beta. This is the symbol beta dash. Size of minimum edge cover. What is alpha? Can you tell me what is alpha? Alpha is size of largest independent set.
Exactly.
Largest independent set. Okay. What is beta? That is size of minimum vertex cover. What is beta dash? That is size of largest matching.
So
Okay.
beta dash is size of largest matching.
That is
It is
alpha.
minimum edge
Alpha
cover,
dash.
right?
Beta dash is size of minimum edge cover,
Yes, yes.
and alpha
Exactly.
dash is size of largest match. Alpha dash, that
Exactly.
is size of largest match. Okay.
Exactly.
So Yuvraj is asking, sir, matching can be defined if any vertex is independent. So one function has perfect matching. I'm not getting your Arpan. Is your doubt clear?
Yes, sir.
Any
Yes,
other
sir.
doubt?
So, one more, there was a diagram. There was a very small diagram. I don't remember the page. So, it was previously. Can you just locate to that once?
Tell me.
Yes, yes, this one.
This is your
Yes,
C6.
yes. So this one, just can you just repeat the how it is happening? The alpha beta I understood. The beta dash and mu I do not understand.
This is C6. This is C6. A, B, C, D, E, F. This is your C6. Now in this C6, let's find out what is alpha. Alpha means largest independent set. Largest independent set. So if you take A, then you cannot take BC. If you take A, you cannot take BC. Then you
Yeah.
can take D, and then you can take E. So the alpha will be equal to 3. And what will be beta? Beta means vertex cover. So if alpha is 3, then beta will be n minus alpha. So that will be 6 minus 3, that will be 3. So beta also will be 3. Basically, what is the largest, what is the smallest vertex cover you can create? Smallest vertex cover. If I take A, then these two edges will be covered. So these two edges are covered. Now, if I take D, then these two edges are covered. Now I have to take E so that I can cover all the edges. So beta will be 3. Next, what is matching? What is the matching? You can notice I can take AB, I can take DF, I can take CE. So the mu will be equal to 3. Okay, and we already know that this relation, we know that mu plus beta
Edge cover.
dash, that is
Exactly.
equal to n. So beta dash will be equal to what? Beta dash will be equal to 6 minus mu. That also will be 3. So beta dash also will be 3. And what is beta dash? Which will cover all the vertices. So you can notice they will cover all the vertices. You can notice these 3 edges will cover all the vertices. So this is your edge cover, minimum edge cover. Okay.
Exactly.
Any other doubt?
Understood. No, sir. Thank you very much.
Any other doubt, anyone? Yuvraj, I'm not getting your doubt. Like, I did not understand your doubt. Please let me know what is the doubt. Hello. Yes, Yuvraj.
Yes, sir, I'm audible.
Yes.
Sir, I'm saying that since matching is independent, edge independent set, then isolated vertices are also allowed, right?
Yeah, isolated vertices are fine.
Then one function must have a perfect matching because one element of domain can like have only one image.
Oh, sorry.
Even if
Like,
like
are you talking about perfect matching?
yes, sir.
Perfect matching. So perfect matching may not exist. There are many
Uh,
graphs for which perfect matching will not exist.
yes, sir, because codomain may have like some element which does not have any pre-image
See,
in
this
one
graph
one
has no
functions.
perfect matching. See, if you notice this graph, for example, this graph does not have any perfect matching. This graph does not have any perfect matching. Okay. For example, any graph on odd number of vertices, any graph on odd number of vertices that does not have any perfect matching. G, V, comma E, where number of vertices is odd. Okay. And even if you have, for example, here you have even number of vertices, this also does not have any perfect matching. So basically all these graphs, okay, like this type of graph, whether you have this graph or whether you have this graph or whether you have this graph, okay, they do not have any perfect matching. Because if you have perfect matching, your number of vertices must be even. But here you have even, but still this does not have any perfect matching. So basically some graphs do not have perfect matching. Like this, they do not have any perfect matching.
Yes, sir.
Is there any other doubt?
No, sir.
Okay. Okay, Viraj. Anyone has any other doubt? Please let me know. So tomorrow we will start this coloring. Okay. This next topic we will start, that is coloring. Tomorrow, coloring chromatic number. In the coloring, we will study chromatic number. Okay. Thank you, everyone.